Welcome to this explainer. Today, we're going to take you right under the hood of artificial intelligence. We hear the term AI absolutely everywhere right now, but today we're going to actually demystify the mechanics of it. We'll explore exactly how these machines learn, how they generate content, and maybe more importantly, what happens when they get things completely wrong. We're kicking things off with this pretty striking quote from philosopher Nick Bostrom. It really sets the stakes for the massive boom in generative AI that we're living through right now. Think about it. Whether you see AI as our ultimate triumph or a profound existential risk, there's just no denying that understanding its anatomy is arguably the most crucial literacy of the 21st century. So, here is our roadmap for today. Number 1, the generative AI boom. 2, inside the neural network. 3, how machines actually learn. 4, transformers and generative engines. And finally, number 5, flaws, biases, and hallucinations. Okay, let's dive right into section 1, the generative AI boom, a paradigm shift. So to understand AI, you have to understand how it's different from everything that came before it. Traditional software is rigid. A programmer sits down and writes explicit, hand-coded instructions. If this, then that. But machine learning completely flips the script. Instead of being programmed, the machine is trained. It uses algorithms to crunch through massive data sets and figure out patterns completely on its own. It's kind of like teaching a kid to recognize animals. You don't hand a toddler a mathematical formula for what a dog is, right? You just show them hundreds of pictures of dogs and cats until they naturally figure out that, hey, floppy ears and a longer snout usually mean it's a dog. The AI learns from those examples rather than strict rules, which is what lets it adapt and actually improve over time.
Moving on to section 2, inside the neural network, the brain of AI. Way back in 1943, a neuroscientist and a logician proposed this mathematical model of an artificial neuron, and they based it directly on how our own brains work. In the human brain, your neurons are connected by synapses that fire off electrical signals, while in an artificial neural network, those artificial neurons are connected by numerical values. They take in inputs, apply some math to them, and pass the result to the next neuron down the line. The network uses what we call weights to determine how strong a connection is, and biases to shift the decision threshold. You can really just think of these weights and biases as tiny little dials that the network is constantly twisting and adjusting to control how it processes data. Now, these artificial neurons don't just operate all by themselves. They stack into this incredibly structured architecture. First, you have your input layer, which takes in the raw data, like, say, the text of an email you just got. Then you have multiple hidden layers sandwiched in the middle. These hidden layers act kind of like a black box where all the real heavy lifting happens, combining bits of information to capture context. And finally, that data hits the output layer, which spits out the final prediction. In our example, it flags whether that email is spam or not. All right, section 3, how machines actually learn, the math behind the magic.
Here's the catch. AI doesn't get things right on the first try. It just doesn't. That's where backpropagation comes in. This was a massive breakthrough in the 1980s that effectively ended a long period of stagnant progress known as the AI winter. Basically, backpropagation is the mathematical engine of improvement. It lets the network measure exactly how wrong its guess was, and then work backwards through all those hidden layers to slightly tweak those dials, the weights and biases. It is quite literally learning from its mistakes, so it can be just a little bit more accurate the next time around.
Every single time an AI trains, it loops through these exact 4 steps. It takes in the data, it passes it forward through the network, that's called forward propagation. Then it measures its error using something called a loss function to see how far off its prediction was from reality. Finally, it uses that backpropagation we just talked about to update its connections. It takes millions, sometimes billions, of these tiny micro-adjustments to turn a random guessing machine into a highly accurate, intelligent system. Let's look at section 4, transformers and generative engines, powering today's tools. As you can see here, different tasks require completely different architectures. Transformers are basically the backbone of modern AI. They compare every single part of an input to every other part to figure out the context, which makes them perfect for generating text. Then you have GANs, or generative adversarial networks. These are wild. GANs actually pit 2 neural networks against each other in a game. You have a generator creating fake images and a discriminator trying to catch the fakes. Because they're competing, they both get insanely good, which is how we get those hyper-realistic synthetic images. And finally, VAEs, which compress data down and rebuild it so we can create highly controlled variations. If we zoom in on transformers, the architecture powering large language models like ChatGPT, it all boils down to tokens and embeddings. You see, AI doesn't actually understand English at all. During training, words get chopped up into machine-readable pieces called tokens. These tokens are then mapped out as numerical embeddings inside this vast, multidimensional mathematical space. This is how the model learns semantic relationships. It basically learns that the word dog lives closer to the word bark than it does to the word tree. So when you type a prompt into an LLM, it's not reasoning with you. It's functioning as a giant statistical prediction machine, just rapidly guessing the most mathematically probable next word based on billions of parameters.
Which brings us to Section 5, Flaws, Biases, and Hallucinations, the dark side. Because these systems are just doing math and lack any actual true understanding, they are highly susceptible to some major risks, and the real-world consequences are already here. Take audio generation, for example. We are absolutely seeing the dark side of AI voice clones. Scammers have literally stolen millions of dollars by synthesizing the exact voices of people's loved ones to make incredibly realistic fake distress calls. It's terrifying. Alongside that malicious use, we have hallucinations, where these models confidently spit out completely false text because, remember, they're optimizing for words that sound plausible, not for factual truth. Add in the massive amounts of energy and computing power they drain, and finally, a very modern looming threat, model autophagy disorder, or MAD. Which leaves us with this massive, pressing question. What happens to AI when it runs out of pristine human-generated data and has to start training on the synthetic data generated by other AIs? Well, that's model autophagy disorder, also known as AI cannibalism. When models train on the outputs of older models, they suffer a rapid, catastrophic degradation. They basically become inbred, churning out absolute gibberish. So I want to leave you with this final thought. As the internet floods with synthetic, AI-generated content, are these brilliant statistical prediction machines destined to eventually choke on their own exhaust, threatening the entire future of machine learning? Thanks so much for joining me on this explainer. Keep questioning the tech you use every day, and I'll see you in the next one.